Welcome back to Examify's IGCSE Physics Revision Series. In this video, we will be diving into Unit 4, Electricity and Magnetism. Electricity and magnetism are among the most powerful forces shaping our modern world. From the lights in our homes to the computers in our hands, from power stations to high-speed trains, all rely on the principles we are about to study. In this unit, we will begin by exploring the basic phenomena of magnetism, learning how magnets behave and how magnetic fields are represented. We will then move on to the essential electrical quantities like charge, current, voltage, resistance, and power, the language of electricity. Apply these ideas to electric circuits, understanding how series and parallel connections work and why they matter. Study the electrical safety, examining the hazards of mains electricity and the protective devices that make use secure. And finally, discover the electromagnetic effects that unite electricity and magnetism, giving rise to induction, motors, generators, and transformers. At the end of this unit, you will not only have mastered the principles of electricity and magnetism, but also see how these ideas connect directly to the real-life technologies that power the modern age. Let us begin our journey into Unit 4. In our first lesson, we will examine the simple phenomena of magnetism. By the end of this unit, you should be able to recognize the properties of magnets, distinguish between temporary and permanent magnets, understand the process of induced magnetism, and represent magnetic fields with clarity. So let us begin. A magnet possesses two poles, a north pole and a south pole. The interaction between these poles follows simple rules. Like poles repel one another, and unlike poles attract. It is important to note that magnetic forces are non-contact forces. They act across space without physical contact. Only certain materials such as iron, nickel, and cobalt respond to these magnetic forces. Other materials such as wood and plastic remain unaffected. Magnets are classified as either temporary or permanent. A temporary magnet is commonly made of soft iron. It becomes magnetized when placed in a magnetic field, but quickly loses its magnetism once the field is removed. A permanent magnet, usually made of hard steel, retains its magnetism for a considerable duration. Soft iron is therefore chosen when we require a magnet that can be switched on and off, like an electromagnet, while steel is preferred when a constant magnetic effect is needed. When a magnet is brought close to an unmagnetized object, such as an iron nail, the object becomes a temporary magnet. This process is called induced magnetism. The end of the iron nearest to the magnet acquires the opposite polarity, resulting in an attractive force. Let's say if the magnet's end is the north pole and the iron nail is attracted to it. The end which is attracted to the north pole becomes the south pole. This is why a magnet can lift several paper clips at once. Each clip becomes magnetized and attracts the next. Every magnet creates an invisible region around it, called a magnetic field. This is where magnetic forces can be felt. We represent this with field lines. They always flow from the north pole to the south pole outside the magnet. When the lines are closer together, the field is stronger. The direction of the field is defined as the direction a small north pole would move if placed in that field. Now, let's do some simple experiments to detect the magnetic fields and the direction of the magnetic fields. Magnetic fields can be detected and mapped in two common ways. One is the compass method. When placed near a magnet, the compass needle aligns with the field. By plotting the directions, the field pattern can be drawn. By sprinkling iron filings on a card placed above a magnet. This method shows the filings aligning along the field lines, producing the familiar curved pattern. Moving further, we are going to the next lesson. In this lesson, we will examine electrical quantities, a foundation of electricity and circuits. By the end of this lesson, you should be able to explain the concept of electric charge, distinguish between conductors and insulators, describe methods of charging objects, represent and understand electrical fields, define and calculate current, potential difference, resistance and power, and interpret current voltage characteristics for common components. Electricity begins with charge. Charge is the fundamental property of matter. There are two types of charge, positive and negative. The rules of interaction between them are simple. Like charges repel one another and unlike charges attract, similar to the magnetic poles. A neutral object contains equal number of positive protons and negative electrons. If this balance is disturbed, the object becomes charged. The SI unit of charge is the coulomb. Although you don't need to know about this fact in your IGCSE physics syllabus, here's a fun fact. 1 coulomb corresponds to approximately 6.25 times 10 to the power 18 electrons. Moving on to conductors and insulators. Materials differ in how they allow charges to move. In conductors, such as copper or aluminium, there are many free electrons which can move easily through the structure. These free electrons are responsible for the flow of current. In insulators such as rubber, plastic or glass, electrons are tightly bound to their atoms and cannot move freely. Thus, insulators do not allow current to flow. This distinction is crucial when designing circuits and electrical devices. Talking about insulators, they can be charged by two main methods, either by friction or by induction. When two insulators are rubbed together, electrons may be transferred from one to the other. For example, rubbing a plastic rod with a piece of cloth causes electrons to move from the cloth to the rod. The rod becomes negatively charged and the cloth becomes positively charged. The second method is by induction. If a charged object is brought close to a neutral insulator, it forces charges within the insulator to rearrange. One side becomes positive and the other side becomes negative. Although the object as a whole remains neutral, this separation of charges explains why small pieces of paper are attracted to a charged balloon. An electric field is a region around a charged object in which another charge experiences a force. We represent electrical fields using field lines, and there are important rules to remember here. Field lines point away from positive charges and towards negative charges. The spacing between the lines indicates the field strength. Closer lines represent stronger fields. Between two parallel charged plates, the field is uniform. Straight parallel lines of equal spacing. Now we will be moving on to current electricity. First quantity of electricity is the current. An electric current is defined as the rate of flow of charge. It is given by the equation I equals Q over T, where I is the current in amperes, Q is the charge in coulombs, and T is the time in seconds. Current is measured using an ammeter, which is always connected in series with the circuit. It is important to note two conventions. Conventional current is defined as flowing from the positive terminal of a power source to the negative. In reality, it is the electrons that flow, which is in the opposite direction from the conventional current. That is, from negative to positive. Currents may be of two types, direct current or alternating current. Direct current has a constant magnitude and flows in one direction only. Examples of direct current are batteries and cells. Alternating current continuously changes in direction and magnitude. The mains electricity supply is an example of the alternating current. Generators are used to produce alternating current, while electronic devices often require direct current. Moving on to the next quantity, we have the electromotive force and the potential difference. The electromotive force of a source is defined as the energy supplied per unit charge by the source to move a charge around a complete circuit. The potential difference across a component is the energy transferred per unit charge as the charge passes through that component. Both quantities are measured in volts, V, and both are measured in using a voltmeter, which is always connected in parallel. The next quantity is resistance. Resistance is the opposition to the flow of current in a material. It is defined as R equals V over I, where R is the resistance in ohms, V is voltage, and I is current. According to Ohm's law, at constant temperature, the current through the conductor is directly proportional to the voltage across it. This is true for ohmic conductors such as resistors. The resistance of a wire depends on its dimensions. It is directly proportional to the length. That is, if the length of a wire is double, the resistance will also be double, and inversely proportional to its cross-sectional area. So if the cross-sectional area of a wire is doubled, the resistance of the wire will be half. The relationship between current and voltage varies with different components. Here we are going to see three main components. Ohmic resistor. The IV graph is a straight line through the origin. This indicates as a constant resistance in an ohmic resistor. Next is the filament lamp. As the voltage increases, the filament gets hotter, increasing the resistance. The IV curve bends, showing that the current does not rise proportionally. Last is the semiconductor diode. Current flows through in one direction, but hardly at all in the opposite direction. This explains why diodes are used for rectification. The last topic in this chapter is power and energy. Electrical power is the rate at which electrical energy is transferred. It is calculated as P equals IV, where P represents the power, I represent the current in amperes, and V represent the potential difference in volts. Or equivalently, this can be also defined as P equals I squared R, where R is the resistance of the component, or P equals V squared over R. The energy transferred by an electrical device is defined as E equals IVT. In household appliances, energy is mainly measured in kilowatt hours. 1 kilowatt hour represents the energy used when a 1000-watt appliance operates for 1 hour. This concludes our lesson on electrical quantities. We have now established the fundamental ideas of charge, current, voltage, resistance, and power. In the next chapter, we will apply these principles to understand the construction and behavior of electrical circuits. Welcome back, Chapter 17. In this lesson, we will examine electrical circuits. By the end of this session, you should be able to recognize common circuit symbols, describe the function of electrical components, compare series and parallel circuits, and perform calculation involving current, voltage, and resistance in these circuits. In physics, circuits are represented using standard symbols. A single cell is drawn as one long and one short line. Several cells together form a battery. A switch opens or closes this circuit. A resistor is shown as a zigzag line, while a variable resistor includes a diagonal arrow. A lamp is a circle with a cross inside, and a diode is a triangle with a line across the one end. An ammeter, circle with A, measures the current and is connected in series with the circuit. A voltmeter, on the other hand, circle with V, measures the potential difference and is always connected in parallel. And finally, a fuse is represented by a rectangle or a small box. As we saw various electric components in the previous slide, now we will be seeing some of the common electrical components' functions. Each component has a specific role in a circuit. A cell and batteries supply the energy to the circuit. Resistors limit the current. Lamps convert electric energy to light and heat. Switches allow current to be turned on and off. Fuses protect the circuit by melting if the current becomes too large. Diodes allow the current to flow in one direction only. Variable resistors adjust the current and are used in dimmer switches or volume controls. There are two more electrical components you need to know in the IGCSE syllabus: thermistor and the light-dependent resistor. Thermistor depends on the temperature. So as the temperature increases in a thermistor, the resistance decreases. Temperature and resistance in a thermistor are inversely proportional. Light-dependent resistor behaves in a similar way, but here there is the light intensity that comes into action. As light intensity increases, the resistance decreases. So light intensity and the resistance are inversely proportional to each other in a light-dependent resistor. Now we will be moving on to the important part of this chapter: series and parallel circuits. First, series circuits. In a series circuit, all components are connected one after the other in a single loop. The current is the same everywhere. The voltage divides across components. That is, V total equals V1 plus V2 plus dot dot dot. The total resistance is the sum of individual resistances. R total equals R1 plus R2 till Rn. If one component in a series circuit fails, the entire circuit stops working. Moving on to parallel circuits. In a parallel circuit, components are connected across separate branches. The voltage is the same across each branch. That is, V total equals V1 equals V2 till Vn. The current splits between the branches. I total equals I1 plus I2 plus dot dot dot. The combined resistance is given by 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3 till 1 over Rn. Parallel circuits are used in household wiring because each appliance receives the full voltage and can be operated independently. Series circuits are simple and require fewer wires, but if one component fails, all others stop working. Parallel circuits are more practical. Each branch works independently. The voltage remains constant, and one failure does not affect the others. This is why all modern homes are wired in parallel. Let's look at some applications of the series circuit. There are mainly two applications, a potential divider circuit and a variable potential divider. A potential divider circuit is a circuit that splits the voltage across two resistors in series in proportion to the resistances. That is, the ratio of the voltages equals to the ratio of the resistance of each component. A variable potential divider is used to control the potential difference across a component. And that brings us to the end of the chapter. Now we will move on to chapter 18, Electrical Safety. Electricity is extremely useful, but can also be dangerous. In this lesson, we will focus on electrical safety, understanding hazards, protective devices, and safe practices while handling electrical systems. First up, we have some hazards of electricity. There are several common hazards. Damaged insulation exposes live wires and can cause shocks. Overheating of cables can occur when too much current flows, leading to a fire risk. Damp conditions increase the conductivity, allowing current to leak through water and cause electrocution. Overloading sockets with too many appliances can draw dangerous levels of current. As we saw some hazards that can be very dangerous when handled inefficiently. Now we will look onto some safety devices that we can use to stay safe. First is the mains wiring and the earth wire. The mains cable consists of three wires: live wire, neutral wire, and earth wire. The live wire, which is usually brown, carries the current into the appliance. Neutral wire, which is commonly blue, completes the circuit by carrying current back. And earth wire, normally green or yellow, provides a safe path for current if a fault occurs, preventing electric shocks. The switch is always connected to the live wire, so that when switched off, the appliance is completely disconnected from the main supply. Next, let's look at a very simple device which we can use to stay safe from electric shocks: fuses and circuit breakers. A fuse is a thin wire that melts if the current exceeds the safe limit. This breaks the circuit and prevents overheating or fire. A circuit breaker serves the same purpose, but is a little more advanced. It uses an electromagnet to trip a switch when the current is too high. Unlike a fuse, it can be reset after the fault is cleared. Lastly, we have the double insulation and earthing. Appliances with plastic casings are designed with double insulation, so no live part can touch the outer surface. These appliances do not require an earth wire. Appliances with metal casings must be earthed. If a live wire touches this casing, current flows safely to the ground through the earth wire, and the fuse or breaker disconnects the supply. This prevents the user from receiving a potentially fatal shock. Now we have arrived at the last chapter of this unit, electromagnetic effects. In this lesson, we will learn about the electromagnetic effects. By the end of this session, you should be able to understand electromagnetic induction, the motor effect, generators, transformers, and the applications of electromagnets. First up, we have the magnetic fields of currents. A current in a wire produces a magnetic field. The field along a straight wire forms concentric circles. The direction is given by the right hand grip rule. If you grip the wire with your right hand, thumb pointing in the direction of the current, your fingers curl in the direction of the magnetic field. In a solenoid, the field resembles that of a bar magnet, with one end behaving as the south pole and the other as the north pole. Adding a soft iron core produces a strong electromagnet. The strength of the magnetic field can be increased by increasing the magnitude of the current flowing in the wire, increasing the number of turns of the coil, or using an iron core to concentrate the magnetic field produced. There are two main applications you need to know in the IGCSE syllabus when coming to the magnetic fields in a current carrying conductor. One is the relay. A relay is used to control a high voltage circuit using a low voltage circuit. And the second one is the speaker. Here, the current passes through the coil, which attracts and repels the magnet connected to the cone, so that the cone vibrates with the air molecules to produce the sound you can hear in a speaker. The next concept is the electromagnetic induction. Whenever a conductor and a magnetic field move relative to each other, an electromotive force is induced. If the circuit is complete, this EMF drives the current. This induced EMF is greater when the magnet is moved faster, or the field is stronger, the coil has more turns, or the coil has the largest surface area. This is a very important law we need to remember. It's called the Lenz's law. Although you don't need to know the name of the law, you need to know where it is applied. The direction of the induced current always opposes the change causing. This is the Lenz's law. For example, if a north pole approaches the coil, the near end of the coil becomes the north pole, repelling it. This preserves the law of conservation of energy. Also, the direction of the induced current, the thumb indicates the motion, the index finger indicates the direction of the magnetic field, and the middle finger indicates the direction of the electric current. Next up, we have the AC generator. This is a component that converts kinetic energy into electrical energy. A coil is rotated in a magnetic field, inducing an EMF across the coil. There are two components of this, carbon brushes and slip rings. These help to conduct the electricity to the output circuit without twisting or breaking the wires. The magnitude of the EMF induced can be increased by rotating the coil faster, using a stronger magnet, or increasing the number of turns in the coil. And a very important question here is why the generated EMF is alternating. This is because the coil moves in a circular path, causing the direction and the angle of motion through the field to change. Maximum voltage is when the coil is horizontal, because the ends of the coil cut the field at 90 degrees. Minimum voltage is when the coil is vertical, because the ends of the coil are parallel to the field. Next, we have the transformer. This is a device which increases or decreases the EMF without losing power. How does it work? An AC voltage is input into the primary coil, which releases an alternating magnetic field. The alternating magnetic field then magnetizes an iron core, changing it through the secondary coil. The alternating magnetic field then induces the AC output voltage in the secondary coil. A very important equation here is the ratio of the voltage in the primary over the secondary coil is equal to the ratio of the number of turns in the primary coil and the secondary coil. During high voltage transmission, voltage is stepped up for transmission cables to reduce the current, which reduces the heat produced by the cables. This reduces the energy loss to the surrounding and lowers the cost of the cables. As we know that there is no loss in power, calculating current in transformers is a very simple equation. The product of the current and the voltage in the primary coil is equal to the product of the current and the voltage in the secondary coil. Power lost in the transmission cables can be also calculated using P equals I squared R. So decreasing the current reduces the power loss by square of that decrease. The last topic in this unit will be the force on a current carrying conductor. Here, there is a way to demonstrate this force. You can use the Fleming's left-hand rule to find the direction of the force. First, place the wire in a magnetic field. Run a current through the wire, and the wire will move perpendicular to the field. The direction of the force can be calculated using the Fleming's left-hand rule. If the current is reversed, the force direction is reversed. If the poles of the magnets are reversed, the force direction is also reversed. Lastly, we have the DC motor. This is a device that converts the electrical energy into kinetic energy by passing a current through a coil in a magnetic field. The end of the coil experiences a force, which produces a moment and turns the coil in this field. The carbon brushes come into action again. The function of the carbon brush is to conduct electricity to the coil without twisting or breaking the wires of the circuit. The function of the split ring commutator here is that it reverses the direction of the current every 180 degrees to keep the coil rotating in the same direction. Without it, the coil would stall in a vertical position. The speed of rotation can be increased by increasing the current or the voltage, increasing the number of turns in the coil, or using a stronger magnet. We have a simple application at the last. It's the force between two parallel current carrying conductors. Magnetic field of A applies a force on B. Magnetic field of B applies a force on A. These forces are equal in magnitude and opposite in direction. This brings us to the conclusion of Unit 4, Electricity and Magnetism. In this unit, we have investigated the fundamental properties of magnets and how magnetic fields are represented. explored electrical quantities including charge, current, voltage, resistance, and power. Applied these principles to series and parallel circuits. Examined the importance of electrical safety and protective devices such as fuses, circuit breakers, and earthing. And discovered the remarkable electromagnetic effect that powers generators, motors, and transformers. All in all, these topics form the foundation of modern electrical technology, from household appliances to global power systems. So congratulations on completing Unit 4. You are now well prepared to connect these topics to the wider world of physics as we move ahead to the next unit. Thanks for learning with Examify. See you soon in the next unit.